Hello, welcome back. In this video, we're going to go over an exercise where we're going to try to understand the limits of the functions at infinity. And at this moment, I want to step back and I want to give you the definition of a horizontal asymptote first. So we say that a horizontal line is a horizontal asymptote of the graph of f when limits of f at infinity minus infinity would be exactly equal to L. So that horizontal asymptote is represented by y equals L. So remember that in the exercise we have three different cases, and for each case we have a rational function. And in fact, there is a good set of guidelines to follow for finding the limits at plus or minus infinity. So first of all, we're going to check the degrees of the top and the bottom of the rational function. And if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is going to be 0 without doing any algebra. If the degree of the numerator is equal to the degree of the denominator, then the limit behavior of the function is determined by the leading coefficients of the rational function. And in the final case, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function doesn't exist. So we're going to conclude it as like DNE, which stands for does not exist. As x approaches infinity, 3x to the power 3 halves divided by 4x squared plus 2. So in this case, we can go ahead and write the degrees of the top and the bottom. So that has a degree 3 halves. And the bottom one has 4x squared plus 2, so two terms we have here. And the highest degree term is x squared. Well, this is degree 2. Going back to one of the cases, we have the degree of the top to be less than the degree of the bottom. So this limit automatically should tend to 0. Why don't we get more rigorous in terms of showing this limit here? I'm showing this to you because in the future we may not have the same type of rational function, and we may have these power terms mixed up with ln functions or sine functions and so on. Why don't we factor out x to the power of 3 halves, 4x to the power of 3 halves of the bottom. So let's see what we have. Well, we have x to the power of 1 half left here. So that this times that would add up to 4x squared plus 2 over this factor here. All right, again, like terms are divided out. There we go. And then at the top I have 3, at the bottom I have 4 times x to the power of 1 half, 2 over this term. So let's let x go to infinity and see what's going on here. Well, first of all, this is a constant dividing an x term here. So this term is going to tend to 0 for sure because you're talking about 2 over a very large number eventually. So this is going to approach 0. And then this term stays as is. And in fact, as x approaches infinity, so this inside the parentheses is going to approach infinity inside the parentheses, right? And then you have a constant here, you have another constant here. So in turn, so you have a constant at the top and infinity at the bottom, so that is going to approach 0. Again, this is us being more rigorous by factoring out the lowest degree term from the top and the bottom. And here we go. Let's just hit the road. So we have this rational function. So at the top, you have 3 times x to the power of 3 halves. In the bottom, you have 4x to the power of 3 halves plus 2. So the top and the bottom are different expressions, and we check the degrees in this case. So the top has only one term in it, and then it's raised to the power of 3 halves. So at the top, we have only one expression, and then x is raised to the power of 3 halves, so the degree of the top is going to be 3 halves. So we have 2 terms in the bottom. One is 4 times x to the power of 3 halves, and the other one is 2. Well, 2 is essentially like x to the power of 0. So if you look at the highest power, it's governed by this term here. And in fact, that has the power. So for this rational function, we fall into the case where we have the degrees of the top and the bottom are the same. So essentially, the limit of this function is governed by the coefficients of, or the ratio of the coefficients of the leading terms. In this case, this term comes with the coefficient 3, and the bottom term comes with this coefficient 4. So then I'm going to conclude that the limit of this function is going to be 3 over 4. Okay, this is us being less rigorous. If you want to be more rigorous, why don't you factor the highest degree term from the top and the bottom and then do some simplification. Again, this is us trying to show 3/4 in a more rigorous way. All right, so x to the 3/2 are essentially the like terms, so we divide them out. And then we let x go to infinity at this moment. Okay, well, there's only one x term left here. This is 2/4x to the power of 3/2. But if x goes to infinity, in other words, as x gets larger and larger and larger, constant 2 divided by this whole infinity is going to tend to 0. So in other words, this term is going to go to 0. And at the top, I have 3. At the bottom, 4 times 1 plus 0. So this would be the value of the limit. And if you simplify that, it's 3/4. All right, let's check out the last case where you have the degree of the top still the same, 3/2, but the degree of the bottom changes because in the bottom you have 4 radical x plus 2. Well, 4 radical x can be written as 4x to the power of 1/2. Since 2 has no x associated with that, so the highest degree term for the bottom is going to be 4x to the power of 1/2. So the degree of the bottom is going to be just 1/2. So now we're in the case of the degree of the top greater than the degree of the bottom. That is going to tell us that this limit, by using our fact that I showed in the first slide, the limit does not exist. Again, let's be rigorous and prove that the limit doesn't exist. Here we go. This time, I'm still factoring out the lowest degree term out of the top and the bottom. Okay, so in the bottom you have 4x to the power of 1/2 factored out. So you have 1 plus 2/4x to the power of 1/2. And at the top, you have 3 times x to the power of 1/2 times x to the power of 1. So in other words, I use some algebra here. Right, I can split x to the power of 3/2 into what? X to the power of 1/2 times x to the power of 1. So like terms are divided out. So here we go, x to the power of 1/2 terms are gone already. So let me just rewrite this limit. All right, staring at this limit and letting x go to infinity, as you see that this term 4 times radical x will approach infinity. 2/that is going to approach 0. Right? Because 2 divided by a huge number is going to approach 0. And 1 plus 0 is going to be 1, and then 4 times that is going to be 4. So the bottom of the rational function approaches 4, whereas the top this time approaches infinity. Because x approaches infinity, 3 times infinity is going to be infinity. So infinity divided by 4 obviously is going to be infinity. When we have the limit infinity, we say the limit doesn't exist. In fact, we're going to need that kind of infinity or minus infinity behavior in the next section. But for the purpose of this section, we just conclude that the limit does not exist. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.